Hello! In the last few videos, we introduced resonance and started to see that thinking only in terms of simple, localized components can sometimes become misleading. Today, I want to focus on one very simple idea, not by explaining it right away, but by looking at it experimentally first. By now, we are familiar with this setup. This is a small Tesla coil, not very powerful, but more than enough for demonstration purposes. As expected, it can light a fluorescent lamp wirelessly when the lamp is close to the top of the coil, but if we move the lamp away, the effect quickly disappears. Now let's change just one thing. I'm adding a thin copper wire to the top of the coil. Thin wire is not connected to ground and it's not connected to anything else. With the system running, the lamp now lights up near almost any point along this wire. So even though nothing has changed, the region where the lamp responds is no longer confined to the top of the coil. Now let's take a step further. I'll connect the lamp directly to the wire, but only on one side. At this point, many people would already say that what we're doing shouldn't work. And yet, the lamp now lights up much more strongly. Now I'll connect the other end of the lamp to a small metal plate. This plate is completely isolated, it's not connected to ground, and it's not connected back to the source. Just by adding this passive object, the lamp becomes a bit brighter and more stable. Nothing about the internal wiring changed. What changed was the physical configuration. Let's pause for a moment and formalize what we've just seen. Instead of looking at the whole setup at once, let's focus on the part whose behavior we're actually observing. This lamp is the object we're trying to understand. It lights up, it changes brightness, and it reacts when we change the setup. From the lamp's point of view, everything that matters happens at these two terminals. Everything else, the coil, the wire, the metal plate, and ever the surroundings, goes inside this box. From here, we don't care about internal details. We only care about how this entire system presents itself at the lamp's terminals. In the experiment, the lamp didn't change. The connections at its terminals didn't change, but when we added a passive object, the metal plate, the behavior changed. That means what the rest of the system presents here has changed. This point of view should sound familiar. In basic circuit theory, ideas like the Thevenin and Norton theorems are built on exactly this perspective. From two terminals, the rest of the circuit can be treated as whatever behavior appears at the boundary. What's different here is that the rest of the system is no longer just what we intentionally wired on a schematic. It also includes geometry, nearby objects, and how the whole setup exists in space. At this point, the schematic alone is no longer a complete description of what the system looks like from the lamp's point of view. So, how should we think about this? In basic circuit theory, there is a very powerful idea behind the Thevenin and Norton theorems. From the point of view of two terminals, the rest of a circuit can be replaced by an equivalent behavior. The important part is not the equivalent itself, but the perspective it introduces. A component does not respond to a schematic. It responds to whatever the rest of the system represents at its terminals. What these experiments show is that once we move beyond strictly local closed circuits, the rest of the system is no longer just what we intentionally wired. It also includes nearby objects, their size, their position, and the overall physical configuration. At this point, the schematic stops being a complete description of what the system looks like from that point of view. So, we haven't introduced a new component, and we haven't explained a new mechanism. What we have identified instead is a limitation. Once a circuit is no longer strictly local, understanding its behavior means moving beyond isolated connections and starting to think in terms of configurations, not just diagrams.